We have two types of curved mirrors in addition to two types of curved lenses. This is a mirror, and if we put our object on this side of the mirror, what kind of mirror would that be? Two names for it. One of them would be it's caved in the middle. It's thinner in the middle than it is at the edges. So we'd say it's a concave mirror. Good. Concave mirror. What's another name for a concave mirror? Converging, right. Now be careful. Let's keep that straight and not mix it up with a concave lens. A concave lens is a diverging lens. So concave mirror, converging. Concave lens is a diverging lens. We got an object here that's beyond twice the focal length, and we know that we can draw two rays in order to figure out what the image is going to look like. First one's going to go from the top of the object down through the focal point. Second one is going to go from the top of the object to the focal point and then parallel to the principal axis. Our image is going to be smaller, it's going to be inverted, and it's going to be real. We know it's real because solid lines intersect, which means that we could, if we wanted to, project it onto a screen. Now, let's draw another object, this time that is much, much closer. This time, let's put our object way over here inside the focal length, right here. First ray is going to go from the top of the object parallel, and then it's going to go down to the focal point. Second ray this time is going to go as if it's leaving the center of curvature, or that point that's twice the focal length. So that ray is going to go from the top of the object away from that, and then it's going to bounce back straight through 2F. In other words, it's going to go back along the path that it came from. Those rays don't intersect, so what we want to do is extend those rays backwards here. We're going to find that they intersect on the other side. The characteristics of this image are that it is larger, it's upright, and it's virtual. Dotted lines intersect. If you want to see the image in this mirror, you got to physically look into the mirror to see it because you can't project it onto a screen. Yep. Well, the rays aren't really intersecting behind the mirror. They're virtually intersecting behind the mirror. Remember what we said when we first introduced refraction, and I drew that picture of the pencil on the board, and I drew the picture of the pond with the fish at the bottom of the pond, and then the diamond, right? Our eyes, or our brains, or whatever it is, whatever the biology of our bodies is, we're always tricked when light changes direction. We always think that light comes from that light has always traveled in the same direction. So in other words, if we're standing over here trying to view this light, okay, we see this beam of light right here as if it's always gone in that direction. So we see that beam of light as if it's started back here somewhere. And we see this beam of light as if it started back here somewhere. Okay, we're not smart enough when we look at something to recognize that that light changed direction. We think if it's going this way, we think that it's always gone that way. So in other words, we think that that beam of light has come from behind the mirror. And because two beams of light are going to intersect at that spot behind the mirror, then that's where we think we see the image. Does that make sense? Okay. Now, let's make a little comparison, draw a little comparison between converging lenses and converging mirrors. If you remember, with converging lenses and mirrors, either one, if the object distance is greater than the focal length, if the object distance is greater than the focal length, then we always ended up with a real image. Right, that last diagram we drew, our object is way back here. We ended up with a real image. That image is always going to be upright. It's going to always be inverted, I should say. And sometimes it will be larger. Sometimes it will be smaller. Sometimes it will be the same size, depending upon how far back that object actually is, how far beyond the focal point it actually is. But whether you're talking about a converging lens or mirror, if DO is bigger than F, it will always have these two characteristics. It will be real and it will be inverted every single time. Now, if DO is equal to the focal length, then we know that there will be no image, whether we're talking about a converging lens or a converging mirror. And if DO is less than the focal length, then we're dealing with an image that is always, regardless of whether it's a lens or a mirror, it's going to be virtual, it's going to be upright, and it's going to be larger. Again, regardless of whether you're talking about the lens or the mirror. So far, we're talking about a converging lens, a converging mirror. It doesn't matter what we got. The characteristics are the same. The one thing that's different about the lens and the mirror, besides obviously how it works, refracting versus reflecting, is that a virtual image for a lens is on the same side as the object. A virtual image for a mirror, you can see in the diagram that you see up on the board right now, is on the opposite side of the mirror than the object is. So that's what's different about the lens and the mirror. This is what's the same about the lens and the mirror. All right, let's draw one more ray diagram here. This is a convex mirror or a diverging mirror. Draw our object anywhere here, and we're going to get the same characteristics. First ray from the top of the object, it reflects away from the focal point. The second one goes down toward the focal point, but it's got to stop when it hits the mirror because it can't go through it. It's going to reflect back parallel to the principal axis. When we extend those rays, they're going to go back like this, and we're going to find that the image is smaller, it's upright, and it's virtual. Dotted lines are intersecting. Doesn't matter where the object is, doesn't matter whether we're talking about a diverging lens or a mirror, we're always going to get, for a diverging lens or mirror, an image that is smaller, an image that is upright, and an image that is virtual. So I want you to be able to draw the ray diagrams. But if you remember these patterns, it sometimes saves you the bother of drawing a ray diagram. Okay, sometimes it's helpful to do the diagram, but sometimes we can just go and kind of think back to the little summary we did up here, and to save ourselves the time of drawing the ray diagram. All right, let's move forward now. A week or so ago, we talked about the mathematics of curved lenses. Today, we're going to talk about the mathematics of curved mirrors. And it's going to go pretty quickly for us because you're going to find that they're almost exactly the same. The first equation that we learned for lenses, we call the thin lens equation. Well, we're going to put another one down here that looks exactly the same as the thin lens equation, but we're going to call it the mirror equation now. So in the context of lenses, it's the lens equation. In the context of mirrors, it's the mirror equation. And then, of course, the other one for magnification, HI over HO equals negative DI over DO. These two equations are exactly the same as they were for lenses. They're used in exactly the same way as they were for lenses. Sign conventions, units, all the same. Centimeters, usually we use for units, but we could use meters or kilometers or whatever we want, as long as we're consistent through the problem. Let's do a quick little review of the sign conventions, though, even though they are the same as they were for lenses. We group our variables into three different groups. F, DO, and DI go together. HO and HI go together. And then the third group is simply the magnification. F is positive if we have a real focal point. And it's negative if you have a virtual focal point. Now, you have a real focal point if you have a converging mirror. And you have a virtual focal point if you have a diverging mirror. It's the same as it was for lenses, right? Converging lens, positive focal length. The only problem here is that a converging mirror is concave, a converging lens was convex. So it's the same sign convention, but the shape of the mirror is opposite to the shape of the lens that produces the real focal point. DO, well, DO is positive if you have a real object, which for us in Physics 30, just like it was with lenses, is going to be all the time. It's negative if you have a virtual object, but you're not going to have, in Physics 30 at least, a virtual object. DI is positive if you have a real image. And when do you have a real image? Well, you can draw your ray diagrams to figure it out. Or you can remember what we said a few minutes ago in our little summary. If you have a converging mirror or lens, it's a real image if the object distance is bigger than the focal length. If it's smaller than the focal length or equal to the focal length, it's not a real image. It's either a virtual image, or in the case where f is equal to DO, there's no image. Sometimes you're told that the image is projected onto a screen. You're not told exactly the image distance or the object distance. You're not told whether it's real or virtual, but if it's projected onto a screen, you know that it's real, and therefore we make DI positive. HO is positive if we have an upright object, which is going to happen 99% of the time. I don't know that I can remember once on any diploma exam where we have an object that's upside down. It could happen, but if it does happen, it would be a rare event. Okay, it's almost always, if not always, right side up. If it does happen to be inverted, the object that is, then we're going to make it a negative value for HO, I should say. Similarly for HI, if the image is upright, then we're going to make it a positive value. If the image is inverted, if the image is inverted, we're going to make it a negative HI. When is the image upright? Well, the image is upright if you have a virtual image, and you have a virtual image if in a converging lens or mirror, try to picture it now, in a converging lens or mirror, if the object distance is smaller than the focal length, or if you have a diverging lens or mirror, it's going to be an upright image. Finally, the magnification, just like it was with lenses, the magnification is positive if the object and image are on the same side of the principal axis. In other words, if they're both upright or both inverted. And it's negative, of course, if one of them is upright and the other one is inverted. The object will almost always be upright. So 9 times out of 10, probably 99 times out of 100, you're able to look at the image. If it's flipped over, M will almost always be negative because the object would have almost always been right side up. Let's take a look at one example here on page 664. It says an object is located 20 centimeters from a converging mirror. I'm going to circle that. I'm going to put positive F. Even though if I forget to do that, I'm going to get away with it because by default, I'll make F positive. I always want to draw attention to it more when I'm dealing with a converging mirror, more as a function of keeping me in the habit of doing it, so that when I have a diverging mirror, I don't forget to draw attention to it. Focal length is 15 centimeters, so we're going to make that positive 15. Where will the image form relative to the mirror vertex? With a lens, we would talk about relative to the optical center. With a mirror, we talk about the surface of the mirror, which is the vertex. So where's it going to form? And if the object is 5 centimeters high, what's the attitude, which means right side up, upside down, the height, and the magnification of the image? So let's say DO is 20 centimeters. Let's say F is positive 15 centimeters. So we want to find DI. We've got HO is 5.00. We want to find HI, and we want to find the magnification. So we got 3 variables. We're looking for 3 variables. Odds are we're going to use both equations. I'm going to start off with the mirror equation. For whatever reason, that's the one I prefer to use. I don't know why. Plug in our numbers, see if we can get something. 1 over 15 is equal to 1 over 20 plus 1 over DI. We're going to say 15x to the minus 1, subtract 20x to the minus 1, and we're going to flip that over. and we end up getting 60. Okay, there's DI. One thing down. Now let's see if we can find HI. HI over HO equals negative DI over DO. HI over 5.00 equals negative 60 over 20. We're going to say HI is neg 15. And then finally, the magnification. Now we can say HI over HO, or we can say negative DI over DO, either one. Get neg 15 over HO of 5, and that's going to give me a magnification of negative 3.00. Sometimes you see a 3.00x or 3.00 times the size of the object, but let's leave it like this. Attitude. Attitude means right side up or upside down. Can anybody tell me whether this is right side up or upside down? What is it, Greg? Why would you say it's upside down? Good. The image height is negative. It's got to be an upside down image. Now, that works 100% of the time. There's another thing that will work 99% of the time. The magnification is negative. Assuming the object was right side up, then a negative magnification means that the image is upside down. The only time that wouldn't work for you is if the object was upside down, then that negative magnification would mean the image is right side up. Okay, but that's a rare event. All right, so we got the attitude. We're not asked for the larger, smaller, same size, but can you tell me whether it's bigger, smaller, or same size? Is this image bigger than the object was, smaller than the object was, or the same size as the object? Same size as the object, yeah. How do you know it's bigger? Okay, if DI is bigger than DO, yes. Or a little bit easier to see when you see that HI is bigger than HO, and we get a magnification that is bigger than 1. Okay? So we know that it's inverted, we know that it's larger, and we know that it's real. How do we know it's real? A converging mirror can produce a real image or a virtual image. How do we know that it's real in this case? Yep. Not F is positive. That tells me that I have a real focal point, right? Doesn't tell me anything about the image. DI is positive, right? If DI is positive, it has to be a real image. The bad news is there's 5 questions that go along with this. I think the first 4 will be, if you had little problem with lenses, I think the first 4 will be pretty straightforward for you. The last one's a bit of a challenge. Okay, we'll see what you can do with that. Okay, we'll give you some time to work on those now, and then we'll take a look at, maybe in another 10 minutes, we'll take a look at one of the questions, give you a little bit more time, and then take a look at question number 5 a little while after that. All right, let's have a look at question number 4. It says a 4 centimeter high object is placed 15 centimeters in front of a concave mirror. Once again, we're dealing with a concave mirror or a converging mirror, which means the focal length is a positive value. What are the image characteristics? Sometimes we call it the attributes, the image attributes or the image characteristics. Using a ray diagram and the mirror equation. Well, we've drawn the ray diagram before, right? We've drawn all possible ray diagrams for mirrors. So we'll just focus on the mirror equation right now. We know that we have an object height that is 4 centimeters, and we know that we have an object distance that's 15 centimeters. We know that we have a focal length of 5.0 centimeters. Listen, what do we want to find here? Let's find everything we can find. Let's find DI. That'll tell us whether it's real or virtual. Let's find HI. That'll tell us whether it's right side up or upside down. And let's find the magnification, and that'll tell us whether it's bigger or smaller. Let's go with DI first. Let's say 1 over F is equal to 1 over DO plus 1 over DI. 1 over 5 equals 1 over 15 plus 1 over DI. Let's figure out what DI is here. We get 5x to the minus 1, subtract 15x to the minus 1. We're going to flip that over. That's not what we're on it. 0.13333. X to the minus 1 is 7.50. So DI is positive 7.50. Right now, even though we weren't asked to find that, we can use that number to tell us that it's a real image. Real image because DI is a positive value. Now let's find HI. Say HI over HO equals negative DI over DO. HI is what we're looking for. HO is 4.0. Negative DI, negative 7.50 over DO of 15.0. HI, I think, is going to work out to be negative 2. Again, we weren't asked to find the image height, but we know that since we found it to be a negative value, then we know that it's going to be an inverted image. Now, I say we should find the magnification to tell us whether it's bigger or smaller or same size. We don't really need that, actually. If we know the object height is 4 and the image height is 2, what do we know about the size of it? Clearly, it's half the size, right? It's going to be smaller. So based on the fact that the image height is smaller than the object height, we know that the image is smaller. You want to find the magnification, it's going to work out to be negative 0.5, tells us because it's less than 1, it's a smaller image. All right, I'll give you a couple more minutes to work on question number 5, and then we'll take a look at that one as a group in a few minutes once you've had that last little chance at it here. All right, let's have a look at number 5 now. It says light from a distant planet is incident on a converging mirror. Once again, we got a positive focal length. The image from the planet forms on a screen that's 45 centimeters from the vertex of the mirror. That's DI, that's the image distance, and we know that that's a real image, even though they don't tell us in so many words that it's a real image. We know that it's a real image because it's projected onto a screen. Okay, if we got a real image, it's projected onto a screen, and we know that we have a value for DI that's a positive value. So we're going to say for number 5, DI is positive 45.0 centimeters. We want to find the focal length of the mirror and the image characteristics. I don't know, man. We got one variable here, and we want to find one variable. It's not too often that we're able to find a variable given one more thing. Anybody make a suggestion as to what I might do here? There's a couple of ways that I thought of to tackle this question. One is a more kind of think about it kind of way, and one is a mathematical way. What do you want to do first? You ready to think, or you ready to do a little bit of math? Let's do some math first then, all right? Let's say 1 over f is equal to 1 over do plus 1 over di. I want to find the focal length. There's only one equation with focal length in it, at least that I have, so I'm going to use that equation. And we call it the lens equation, or in this case, I guess it would be the mirror equation. I want to find the value of f, but I got a problem because I don't know what the value of do is. Let me ask you this question, though. Okay. Peyton, what's 1 over 1? Good. What's 1 over 2, Matt? 0.5. Good. What's 1 over 3, Caitlin? 0.333. Okay, and so on. 1 over 4 is 0.25, and so on. As the denominator gets bigger, then the number gets smaller. We don't know how far away this planet is, but we know that the object distance is big. It's really big. 1 over 4 is 0.25. 1 over 10 is 0.1. 1 over 100 is 0.01. 1 over 1,000 is 0.001. 1 over a really, really, really big number is effectively what? Somebody said it? It's effectively 0. It's not exactly equal to 0, but effectively. So we're going to say 1 over f is equal to 0 plus 1 over 45. And that means the focal length is 45 centimeters, same as the image distance was. Now, let's look at it the qualitative way, kind of the thinking way here. Remember the activity that we did yesterday? I had you guys find the focal length of a converging lens. This is a mirror, okay, but lenses work real similar to, at least with sign conventions and how we find numbers and so on, real similar to what we have with mirrors. You guys focused on a far off object in order to find the focal length of the lens. Why did you pick a far off object as opposed to a close by object? because the rays of light that were coming off of that object far off and that made it through the lens were parallel to each other and parallel to the principal axis. There's not much else that's further away from us than a planet. So if we focus our lens, or our mirror in this case, on the far off planet, then those rays will be parallel to each other and parallel to the principal axis. Where are they going to converge? At the focal point. And just like the rays of light that were reflecting off of the condos across the street, or the flagpole on the other side of the football field, or the condos over there, those rays were parallel, converged at the focal point. These rays are parallel and they're converging at the focal point. So if they converged at 45 centimeters, then they're converging at the focal point of 45 centimeters. Now, what about the characteristics? First of all, we know it's real. We know it's real right off the top because we have an image that's formed on a screen. Larger, smaller, same size. Well, let's say m is equal to negative di over do. Di is negative 45 over the big number. The magnification is negative 0 point something, right? In other words, the image formed is going to be smaller. Does that make sense? Think about that for a second, though. You ever look in a telescope? You ever look at a telescope? Doesn't it magnify things? Doesn't it make the planet bigger? No, it doesn't. It allows you to see something far off, but it's not bigger. If you look in a telescope and you can see the entire planet in a telescope, is the image bigger than the object? The object is a heck of a lot bigger than the telescope. If the image is formed completely within the telescope, then the image is smaller than the object. It just allows us to see something further away. It doesn't make it bigger. It just allows us to see something farther away. So it is going to be a smaller image than the object is, and we know that it's going to be inverted as well. And we know that because the magnification here would be negative something. And assuming the object is right side up, then the image would be upside down with a negative magnification.